Hey there, Algebra 2 students. Welcome back to Miss McGuire's classroom. Today is our second to last lesson of the entire school year. How crazy is that? So we're going to be doing Unit 7, Lesson 8. Our main topic is solving log equations. Don't forget to put your first and last name, period, and the date in the upper right-hand corner of your paper real quick. Our objective today is I will solve exponential and log equations by using log properties. Mastery will be demonstrated by scoring at least 80% on the extra practice. So there's a couple different scenarios that we're going to have. And one of those scenarios when we solve log equations is you're going to see equations where you have a log equal to a log. So as you can see, I have log base 15 is equal to log base 15. There's things in this log, of course. I have log base 15 of 4 minus p. It's equal to log base 15 of negative 2p minus 2. And what's really neat, though, is if you have a log equal to another log, you can actually drop the logs and set what's inside the logs equal to each other. So 4 minus p would have to be equal to negative 2p minus 2. Now, please note, you're only allowed to do this if both of the logs are set equal to each other, there's something else going on in the equation, and the bases are the same. So let's solve for p. Let's see, let's add 2p to this side. Let's subtract 4 to that side. We're gonna get 1p is equal to negative 6. And then we want to plug it back into our equation just to make sure that it works. You know, we always got to check our answers. So we're going to have the log base 15 of 4 minus negative 6 is equal to the log base 15 of negative 2 times negative 6 minus 2. And the log base 15 of, what is that? 4 minus negative 6 is 10, is equal to the log base 15 of 12 minus 2 is 10. So the log base 15 of 10 is equal to the log base 15 of 10. Those two things are in fact the same. So the reason why we needed to check that is because we are not allowed to take the log of a negative number, because remember how, like, if you have the log of 2, I don't know, of log base 2 of negative 16 equals x. 2 to the what power would give you a negative 16. 2 to the what power is a negative 16. There is no exponent that you can take 2 to the power of and get a negative number. So you're never allowed to have a negative in your logs. So when you're solving log equations, you always want to plug them back in, make sure they work, and make sure that whatever's in the log ends up being a positive number. So p is equal to negative 6 will definitely work. All right, log of x squared minus x is equal to the log of 4x. Are these logs, do these logs have the same base? Yes or no? So both of these logs are base 10, so they do have the same base. So you can take what's inside the log and set them equal to each other. Now, why don't you go ahead and try solving for x? You've got a degree 2 polynomial. You want to make sure it's equal to 0. You'll probably be able to solve it by factoring. You're going to find 2 answers. Make sure you plug both of those answers back into the original equation and check it out. Go ahead and give this problem a shot on your own. See what you get. All right, so hopefully you were able to solve this equation on your own. We've been doing these types of equations all semester. I just, factored x squared minus 5x. I put each factor equal to 0, and I got 2 answers. I got x equals 0 and x equals 5. When I checked x equals 5, by plugging it back into the original equation, I got the log of 20 equals the log of 20. But we need to talk about x equals 0 as a solution. When I plug x equals 0 back in, I get the log of 0 squared minus 0 is equal to the log of 4 times 0. So 0 squared minus 0 is 0, so the log of 0 would be equal to the log of 0. However, we need to double check, just like if you take the log of a negative, is it okay for us to have the log of 0? So when you think about what the log of 0 means, the log of 0 means that 10 to some power is equal to 0. 10 to what power would be 0? If you take your calculator and you plug in any number for x, 10 to the first, 10 to the 0, 10 to the negative 1, are you going to get anything equal to 0? Well, we can actually take our calculator and just double check that our suspicions are correct. And take the log of 0. And what does your calculator tell you? Your calculator should give you some kind of error message. Taking the log of 0 isn't allowed. So because taking the log of 0 isn't allowed, that means x can't be equal to 0, and our only solution is x equals 5, because it's the only one that works. So maybe we should just make a note at the top of our notes here. We can't take the log of 0, and we can't take the log of negative numbers. Just things to keep in mind. Because remember, logs are really just powers. So an algorithm defined different powers. What to the any base to what power would ever get you 0? Any base to what power would ever get you a negative number? It just doesn't work. All right. And one more, part C. So we have the log of negative 3x minus the log of 3 is equal to the log of 35. And you might say to me, well, Ms. McGuire, we can't solve this equation because we've got 2 logs on this side equal to a log. And to be able to solve these equations, we need a log equal to a log, not 2 logs equal to a log. So what do? Well, is there perhaps a property of logs that would allow us to take 2 logs that are being subtracted and combine them into 1 log? I think that there is a property called the quotient property that would let us rewrite this log as the log of negative 3x over 3 is equal to the log of 35. Now, why don't you go ahead and finish this problem on your own, and I'll see you on the other side. All right, so when you solve this thing, you should end up with x equals negative 35. And you might think, oh, Ms. McGuire, x can't be equal to a negative because you can't have a negative inside a log. But hold on a second. When you plug it back into the original problem, you would get the log of negative 3 times negative 35 minus the log of 3 is equal to the log of 35. Well, what ends up happening is you're going to take this divided by this and put it into 1 log. So negative 3 times negative 35 divided by 3. 3 divided by 3 cancels, and a negative times a negative gets us a positive inside the log. So we can plug negative 35 into this log. And we get the log of 35 is equal to the log of 35, which checks out. So x is equal to negative 35. All right, so example 2, we're just going to dive right into some equations that have x as an exponent, and we need to discuss what to do in these cases, how to solve for x when it's in the exponent itself. And then I'm going to show you how to use logs to get the variable out of the exponent. Give me 1 second. Oh, just kidding. Let's remind ourselves what the power property is. So the power property is going to end up helping us solve some of these equations as we move forward. Remember, the power property says that if you have a log base b of m to the nth power, you can take that exponent and bring it out in front of the log and multiply it by the log. So you get n times the log base b of n. So logs let us kind of get rid of or deal with exponents and change it into multiplication. All right, so let's deal with some problems. So in an earlier lesson, I mentioned that if you have a power with the same base equal to a power with the same base, I think I just said that funny. If you have two powers with the same base equal to each other, so like 3 to the x is equal to 3 to the 4, if the bases are the same, then that means that the exponents are also the same. They're equal. So you just take the exponents and set them equal to each other. So x would be equal to 4. So we would have 3 to the 4th is equal to 3 to the 4th, which makes sense. So x is equal to 4. All right, what about 2 to the x equals 256? So we need to see, can we rewrite 256 as a power with a base of 2? We want the bases to be the same. So 2 to the x would be equal to 256. How can I rewrite that as a power of 2? Go ahead and do that for me. So we can rewrite 256 as 2 to the 8th. Check it out. Our powers now have the same base, which means the exponents themselves must be equal. So x is equal to 8. When I plug that back in, 2 to the 8th is equal to 256, which is true. All right, what about 16 to the 3x equals 8? You need to rewrite both of these as a power with the same base. And I'll give you a hint. You want that base to be 2. Go ahead and give this a shot. All right, so you should have gotten 2 to the 4 rewritten is 16 rewritten as a power of 2. 2 to the 3rd is 8 rewritten as a power of 2. So 2 to the 4th to the 3x is 2 to the 12x equals 2 to the 3rd. Now that the bases of these powers are the same, we can go ahead and set the exponents equal to each other. So 12x is equal to 3. Solving for x, we get x is 1/4. All right, go ahead and do part D. Rewrite 27 and 81 as powers of the same base. Once you've had that done, you can set the exponents equal to each other and solve for x. All right, so we have x equals 4/9 as our final answer. Now let's look at part E. So for part E, 7 to the x equals 49. For some reason, I thought these weren't going to be able to be rewritten as powers of the same base, but they totally can. Because what's 49? As a power of 7. 7 to the 2nd, which means x would be equal to 2x. Or just kidding, x would be equal to 2. I just messed up with these problems. Fun times. All right, so part F, 7 to the 4x is equal to 800. So now we're going to ask ourselves, can 7 to the 4x and 800, can we rewrite 800 as a power of 7? So if I take 7 to the 2nd, I'm going to get 49. If I take it to the 3rd, I get 147. Just kidding. Let's pretend like I didn't just do that. 7 is 49 times 7. I would get 343. Then we're going to multiply that by 7 again, taking it to the 4th power. We get 2,401. And we see that we can't get 800 as a power of 7 because 7 to the 3rd is too little. 7 to the 4th is too high. So we're not going to be able to rewrite this as a power with the same base. So, and have like an integer exponent is what I'm trying to say. So what we're going to have to do is we're going to have to use our power property to help us and use logs to help us solve this equation. So check this out. If I take this equation and I take the log of 7 to the 4x is equal to the log of 800. So the reason why I've done this is because if you recall, our power property lets us take an exponent. As long as we have logs present, we can take an exponent and bring it out in front of the log and change it to multiplication. And this is going to come in handy because our x is an exponent. And so to bring it out from being an exponent, I want to use logs so I can use the power property. You have to have a log present in order to use the power property. So if I take the log of one side of an equation, to keep it equal, I have to take the log of the other side as well. So what I've done is I've just taken the log of both sides. Now, because a log is present, I can take this exponent and move it out in front of the log using the power property. So 4x times the log of 7 is equal to the log of 800. Now we can solve for x because x is being multiplied by 4 and the log of 7. How do I cancel multiplication? I simply divide both sides. I divide 4 and I divide by the log of 7. So notice I also used the log base 10. So I divided the other side by 4 and log 7. There we go. So I used the log base 10 because that's the log that my calculator uses. So I can take this, plug it into my calculator, and then find our answer. So x is going to be equal to, and I want you to listen carefully. When you solve for x using logs, you need to round to the 4th decimal place. So you're going to take the log of 800. You're going to close those parentheses of the log. Just kidding. Here we go. The log of 800. There we go. Divided by, and then you're going to do open parentheses. You're going to do 4 log 7. You're going to close the parentheses of the log and close the parentheses of the denominator of that fraction. That way the log of 800 gets divided by both the 4 and the log of 7. So then we get 0.8588. And so we don't have to worry about rounding. We're going to have 0.8588. Now, when you check your answer, so let me move this for a second. All right. When I check my answer, I'm going to take 7 to the 4 times 0.8588 is equal to 800, and we're going to see if that's right. So 7 to the 4th times 0.8588 is 799.98, and that would round up to 800. So this decimal, because it's rounded, doesn't give us like the perfect answer when we plug it back in, but it gets us close enough that if I round, I do get up to 800. So that's why I ask you to go round to the 4th decimal place with these, because we don't want to mess up when we plug it back in, like, and have a rounding error and not get close enough to the number that we're looking for. All right, so 5 to the 2x is equal to 130. Can we rewrite 130 as a power of 5? The answer is no. 5 to the 3rd is 125, and 5 to the 4th is over 130, so that's not going to work. So instead, we want to use the power property so that we can bring x out in front of our log, and it will no longer be an exponent. To do that, though, we need a log. So you're going to take the log of both sides. What you do to one side, you have to do to the other. And then you're going to solve for x. So use that power property, bring that exponent out in front of the log, and solve for x. Remember to round to the 4th decimal place. Go ahead and finish that problem on your own. All right, so you should have gotten x equals 1.5122. When I check that answer, I'm going to take 5 to the 2 times 1.5122 5122, and I get 130.006. So that would round to 130. So it's an approximation, and that will get us as close as we can to the right answer. All right, go ahead and do part H completely on your own. You got this. All right, so you should have gotten x equals 1.2114. All right, so now we're going to be able to solve for the time in our exponential growth and decay functions, whereas before we had to estimate them. Now that we know how to use logs to solve for a variable that's in an exponent, we can apply this to those problems, and we don't have to guess and check anymore like we did in, that was like 3 lessons ago, I think. So, what is a sustainable, renewable, natural resource when you manage forests properly? Your lumber company has 1.2 million trees. You plan to harvest 7% of the trees each year. How many years will it take to harvest half the trees? So remember, when you talk about exponential growth or decay, you use the equation y is equal to a times b to the x. Your growth rate is 1 plus r. Your decay rate is 1 minus r. So in this case, we're losing trees, so we are going to use exponential decay. So our total number of trees is equal to, our initial value of 1,200,000 times 1 minus our rate of 7%, so 0.07, to the lowercase t for time. So we don't know how many years. We're trying to figure out how many years it will take to harvest half of the trees. So we're going to solve for t. Now the total number of trees will end up being, in whatever time that is, half of our original amount. So half of 1.2 million would be 600,000. So we're going to plug in 600,000 for our new total. And we are going to solve for t. So what I recommend you do is go ahead and take 1 minus 0.07, which I believe is 0.93. And then what I would do is I would go ahead and divide both sides by that 1.2 million. And then doesn't that reduce to a half? I'm just afraid of making mistakes. So I'm going to go ahead and say 6 divided by 1.2. Just kidding. I should have done 0.6 because it's 0.6 million. Divided by 1.2 million is, yeah, a half. So 600,000 divided by 1,200,000. Same thing. Yep. Okay. So this will end up being 0.5 is equal to 0.93 to the t. Now, if our exponent, our variable is in an exponent, how do I get that variable to no longer be in the exponent? I use the power property. But to be able to use that, I need to have a log present in the equation. So I'm going to take the log of both sides. So I'm going to get the log of 0.5 is equal to the log of 0.93 to the t. I'm going to use the power property, bring that t out in front of this log. So I'm going to have the log of 0.5 is equal to t times the log of 0.93. Then we're going to divide both sides by the log of 0.93. And we're going to get t is equal to, so we're going to take the log of 0.5. And we're going to divide it by the log of 0.93. We get 9.551, We're talking about years, so it's okay to round to the nearest decimal place, the 10th decimal place. So we could do 9.6. And of course, we're talking about a word problem where context means everything. So we're going to want to make sure that we write a little sentence for our final answer. We're going to say in 9.6 years, half of the trees will be harvested. All right. Now for part B. After how many years will you have harvested half of the trees if you harvest at a rate of 5% instead of 7% yearly? So you're going to set up the same equation, except your decay rate is changing to 5% instead of 7%. So go ahead and plug that into your equation, rewrite it. You're still looking at having half of your trees harvested. How long will it take if you're harvesting them at a slower rate? And see what you get. Go ahead and finish that problem on your own. I found that if you are harvesting at a rate of 5% annually, it's going to take 13.5 years for half of the trees to end up being harvested. So if you slow your rate of harvesting by 2%, it's going to take an extra, like almost 4 years to lose half of the tree population. All right, make sure you get your extra practice done. When that's done, let me know. We'll go over it together, and I'll see you back in class. Have a good day.